thank you all for joining our Ask Mayfield Anything. For those of you who don't know me, my name is Ryan Mayfield, founder and owner of Mayfield Renewables and host for our Ask Mayfield Anything series that we do. And, real quick about, our company. I founded the company in 2007, so just over 15 years ago now. And, we're really intent on providing education and our expertise to the industry for EPCs, manufacturers, and contractors. So, we hold these monthly AMAs with the intention of talking about topics that are important, that are, timely for the industry. And so today we'll be talking about microgrid systems. And, we want to use this as a way to connect with our network and the industry in order to help kind of bring some of that expertise to you. And so our mission, we provide services, engineering and design services for solar and solar plus storage systems, consulting for both manufacturers through product releases, and then also for EPCs, doing systems, microgrid feasibilities, project consulting, things like that. So if there's any of those things that we can help you with, feel free to reach out and we'd love to talk. So with that, I want to introduce, and I'll let our today's guests introduce themselves, give them a little bit of background here. But Roberto and Michiel, goes by Mac, are joining us today to talk about microgrid systems, kind of protecting that investment. And so Roberto, VP of Engineering over at ELM. So why don't you just give us a little bit on your background and kind of your perspective.
Sure. Thank you, Ryan, and welcome everybody. Yeah, my name is Roberto Muniz, born and raised in Puerto Rico, with over 15 years of experience working with the utility world, a lot of electrical installation, inspection, and construction. In the past 2 years, I've been working as the director and VP of engineering here at ELM companies, manufacturing battery energy storage solutions.
Great. Thanks for joining. I think you're going to have from your perspective, from ELM, have some great insight on what you've been seeing being installed and putting into use on these microgrid systems. So Mac, you want to introduce yourselves for us?
Yeah, absolutely. Welcome everybody. My name is Michiel Zuidweg, or Mac, much easier. Senior microgrid specialist at Mayfield Renewables. Been in the renewable space for 22 years or so, but now just focusing on microgrids and really diving in deep on feasibility studies and then also using them all the way to commissioning and implementation. So I'm really excited to be here for this AMA.
Great. Thanks for joining us. Yeah, and so Mac brings a lot of expertise to the conversation. I'm excited that you were able to join. And kind of help us go through these as we are, in the throes of doing some feasibility studies, system designs, and so being able to see it all the way from conception through commissioning is helpful. Okay, so today, we're talking about proper planning to protect microgrid investments, and so the microgrids are complex. They're we're seeing a lot of up and coming, I guess you could say, we're seeing a lot more interest in these. And so before we jump in, this is a topic I wanted to throw out there, bring up, and get our guests' input here. But defining microgrids in of itself is kind of a process, I guess you could say. And so when we start talking about microgrids, there's a code definition, there's DOE definition. So it depends on what the actual application is going to be. And so, in short, microgrids we're taking multiple power generation sources. Typically, we have solar, maybe we have wind, we have generators, we have these power sources that are not the utility. And we are typically interconnecting with the utility, but part of many microgrid definitions or part of microgrids are going to be this resiliency aspect. it's not necessarily 100% resiliency. Maybe it's just a small portion of the system is for the resiliency. But we have all of these different components coming in, getting controlled and working together to provide power to loads. So Mac, I think when we were talking yesterday, I mean, you had some good insight, I think, on, definition of microgrid and just kind of how those different systems can interplay with each other.
Yeah, the classical term of microgrids is exactly what we've, used to think of them as 20 years ago, is like actually creating that grid for a community out somewhere. But now it has so many more definitions, and a lot of people think of it as just a resiliency project, but a lot of the clients, that we work with, it's not as much about resiliency, but it's more about financials. When you have time of use rates, peak demand, but then you also get to work with the ITC makers, SCHIP funding, or other DR programs, then it becomes not just a resiliency project, but a financial project that's hopefully reduces the net operating income of a business. And for one recent client in Northern California, it was evaluating a system to what the return on investment is just to reduce their net operating income, but there was no way that the system was still going to have good capacity for resiliency. And then another one that we often see too out on for certain type of large users like cannabis growers, small green growers, is that maybe the utility is can't provide the service size that they need. So you do a mix of service from the utility, and then you can increase the service size to the building by doing an additional microgrid with its own islanding capabilities, etc. So there's multiple purposes for these microgrids instead of just resiliency.
Yeah, and so it was interesting, like that prospect, I guess, of augmenting the utility was interesting to me. Of you can only get a service size of a certain amount out to a site, and so yeah, using other generation sources as kind of that to help augment and not necessarily even creating a microgrid, as I would. Again, this gets into our own personal definitions and how we look at it, but it was a interesting way of looking at that or thinking about that in terms of how microgrids are defined.
Mm-hmm. Yeah.
And Roberto, I mean, I feel like we talked to you about some of these, and I think some of the, if correct me if I'm wrong, but some of the systems you all are doing are, you're looking at demand response and things like that as well, and so that kind of falls into the microgrid. And I think if you want to get super technical, if it doesn't have that ability to island, is it truly a microgrid? I mean, but all in all, we're seeing these larger systems go in with multiple uses. And I think that's something that ELM is seeing quite a bit. Is that right?
Yeah, correct. I mean, microgrids, and to add to your first point, the definition of microgrids based on the past years from utilities, where they consider a microgrid island in a specific community or a small generator plant from the bigger grid. They also consider that as a microgrid rather than the distributed generators or generation that we have now with renewables. And yeah, based on our experience, we are seeing more projects now to have our smaller microgrids, and we can consider extra generators like PV, battery energy storage with their controls to do the demand response, peak shaving, non-wires alternatives, which is another option for bigger utilities. They realize that replacing a substation that is remotely built and is falling short because of the demand, adding more of these smaller microgrids contribute to their financial analysis. Just doing peak shaving, they cannot be islanded because it might not have the capability of supply the whole load, but is contributing to that portion.
Yeah, can I add on to that peak demand?
Yeah, absolutely.
Yeah, so as two examples, there was a client that was in an ISO out in the East Coast. Their main purpose of this microgrid was peak load share, where in the summertime, you have these 5 summertime events that are scheduled. And depending on what your peak demand is at that specific time is how they determine what, how much you stress the transmission lines and how they're going to charge you the following year on your demand charge. So they had a microgrid designed to, at those specific 5 days, to dramatically reduce their demand at that time. So then the following year it dramatically reduces their peak, their demand charge. Or another example is a local utility here in Washington. They did a microgrid specifically to divert substation and underwater cables between substations and the San Juans. So if they didn't reduce that peak demand, then with all the growth in that area, they're going to have to spend a lot of money to replace those cables. But with this microgrid, they were able to divert that for 20 years. So, a lot of financial benefit as well, besides just resiliency.
Right. So yeah. So like you were saying, a lot of times it becomes a financial system or a system built around finances and making systems work. Helping the users, whoever that is, the utilities or the end users, to financially better their situation.
Mm-hmm.
Okay. So with that, let's talk about, getting into planning microgrids. And I think that's a big focus for what we are doing here at Mayfield. It's we're definitely doing a lot of support on that. But I guess I'd like to have the two of you talk to me about, kind of those first steps, even like, what are we doing? And Roberto, I mean, we've talked about, and we'll probably bring this up again in the equipment section, but, getting to the end of the project, getting towards the commissioning stage, and then realizing that customer expectations versus what the delivery is going to be are maybe two different things, or, that the communication didn't happen well. So very often we've already talked about the financial side, the resiliency side, but defining the use case, client expectations and priorities. So Mac, I know you and I have been involved in some of this. We're working with the local city here. And so I guess talk to me a little bit about that process for you. What does that look like? And, helping define what that use case is.
Yeah, really sitting down with the client to chat about the priority goals and performance requirements of the system, and defining that, but really spending the time to define that. Because as soon as you start looking at the load profile, whether it's a 15-minute interval data, hopefully, and then you're looking at the tariff rate structure, we need to have deep conversations about future load growth, maybe future rates with the utility. How does the facility operate every single day? Do they have regular hours? And then, of course, just looking at the load profile isn't enough of the answer. We have to look at what the actual loads are. Because on a 15-minute interval data, right, that's an average over 15 minutes, and it doesn't necessarily incorporate some surge. So looking at the loads, looking at pumps, compressors, motors, and getting on site, looking at electrical drawings, and then like the panel schedules to get additional loads, to really understand what's expected, and then defining that use case. And I think, on a previous discussion, Roberto, you had a good comment about defining that use case.
Yeah, correct, Mac. And specifically on the use case, once you have that load profile well defined and you understand the capabilities or the size of an equipment, the use case is very important, right? If you want to do a small, let's say you want to do a peak shaving, right? And the peak shave was determined to be over a maximum of 15 minutes. You want to do a maximum, discharge or provide power to a big load within 15 minutes, rather than when you do that over resiliency, that you are supplying a load for a longer period of time. You're using different operations there. So it's very important that you understand what's going to be the use case to properly design the system, size the system that you're going to use.
So with that, in mind, and you talked about the load profile. So I guess we've gone a couple different routes and looking at that load profile and trying to determine that. So I know that some utilities make that data available that you can go through and get different schedules from the utilities. But Mac, I mean, in terms of your point of getting that 15-minute data, how do you go about understanding what those peaks are? I mean, gathering 1-minute data, I guess, would be helpful, but is maybe too much data. So I guess, what's that balance? And then kind of on that other side is, how are you, because I know you do a lot of the modeling and you're doing that with us. How do you stretch that, short amount of time? If you only gather a little bit of data, how are you stretching that over the course of the year?
Yeah, great question. I guess part of it also depends on what kind of feasibility study are we looking at, and there's a high level view, or getting a bit more detailed. Are we going for grant funding, or are we definitely, is it are we trying to decide, is it go, no go, or are we really diving a bit deeper? And so I'd rather have at least 15-minute interval data for an analysis. And then depending on what the building or the structure is used as, then I might actually want to have just like a 30-day load study to really get a look at maybe 1-minute intervals to get an idea of what the surge is, at that facility. And these, that does accrue some costs. You can install metering devices to get that 1-minute interval data. You can do a 30-day load study of 15-minute intervals and then extrapolate that over the year. And even with these programs of Microgrid and Zendy, you can do synthetic load profiles. I mean, the synthetics are okay to like get a general idea, but if you really go into the detailed design, then I'm not quite sure I would rely on the synthetic loads, just because they tend to be quite different than real life situations. But the metering devices are incredibly helpful to really understand how the facility operates, but it also depends on the type of building. And I know there's always a budgetary constraints. It's hard to spend money on feasibility studies, but I tend to find that often the range for a feasibility study is maybe 0.5% to about 2% of the project cost. But I can guarantee you, with a good, thorough feasibility study, you're going to save more money in the long run than the money spent on that feasibility.
Yeah, and that's it. I mean, that's a good point. So we get that quite a bit. So obviously doing a good study up front, there comes in, there's a cost associated with that, right? Mm-hmm. And so being able to strike that balance, and this is kind of Robertson in a question, kind of, how do you strike the balance of, somebody who may not see the worth or the return on this investment, exactly. And I mean, we have some personal experiences for sure. I mean, everybody on the call has been involved in projects where something like this wasn't done, and then when it gets to construction time, you're having to make changes. Construction changes are expensive, and so I guess I don't know. Do you have a good answer, Mac, in terms of that pushback on terms of this is going to cost money, it's going to take time? I don't feel like we have a.
Yeah, that's a hard one to answer for sure. But, any investment takes requires some form of feasibility, right? If you're doing this as an investment and you're trying to look at the IRR, internal rate of return, whether you're going to invest in just a generator, what's your IRR? And if you're going to invest in a microgrid, what's your IRR? And then you can compare those two together, and whichever one has the higher internal rate of return, then is the better investment, right? The other thing that I want to say is I'm surprised with how many times I need to reference a thorough feasibility study, because over the timeline of a microgrid, when you go from the feasibility to design to permitting to implementation and commissioning, products change, codes change, loads change, tariff structures change, and then you're going to have to go back to reference that, make some tweaks and edits, or be able to answer quick questions, hopefully, based on the initial study. And if you don't have that good foundation, then things start to quickly fall apart. So it's hard to sometimes invest, but it's always fully worth it.
Yeah, and like I said, I mean, we've definitely seen, and I mean, we can definitely put some dollars to, construction changes, for example, and things like that. And that's definitely something we can do. But, just being able to, there's the time element of that and just the hassle factor. And so there's, always more to it than just the equipment change or something like that.
Mm-hmm. Yeah. And then, part of the defining the use case and clients' expectations is also defining the life of the project. The lifespan, whether it's going to be finance, cash purchased, if it's going to be there's going to be a grant involved, and understanding that might also change some of the system parameters and how you would approach the microgrid. And these are all of that comes into some of the deliverables of the feasibility report.
Right. So Roberto, I mean, how much is ELM are getting involved on that, or is that what is your as a manufacturer, kind of what's your expectation, or what is it, or I guess maybe not even expectation, what's your hope, or what do you guys like to see, or is there a requirement that you have in order to when you're going through and helping spec out system components?
Sure. So one thing that we emphasize is in explaining our customers our product capability, by explaining that we want to align the customer expectations with their equipment and making sure that if they want to achieve a specific use, a specific application, that not only our equipment is compatible, but that the customer understand that they might be the need of additional equipment. We're talking about probably, more meters across the site, more communication components and things like that, more resilient disconnect means, things like that are not always provided by us, but is part of the integration of all these sources. So we definitely spend time with customers up front, aligning their expectation with the equipment capabilities, and we provide some recommendations on how to achieve that.
Great. Okay. Yeah. And I mean, I know we definitely, working with different manufacturers, trying to get them on that, in that conversation early is an important aspect as well. Okay. Anything I missed here on this one that you guys wanted to talk about?
Yeah, I think that part, involving vendors and product manufacturers within that first phase is very important, because we're not talking about a single product. Sometimes we're talking about a solution that is based or is basically composed of different components working together, and understanding the complexity of it, the operation of the system at the end, because sometimes you're not accounting for human intervention, or it's going to be totally automated, how you achieve that. So I think it's very important to understand, after the use case is defined, the complexity of the system and how you're going to operate the system once it is already installed and commissioned.
Wonderful. Yeah, I think those are all great points. And I think as we're going to talk about some of the equipment stuff here, and I mean, that's always a challenge, right? Just the consistent changes, if anything's, we're constantly seeing new equipment, things like that. And so having those conversations and knowing, from your manufacturers as well, this project is not going to start for another 9 months. And if you want to be planning around equipment that's going to be obsolete or, being modified in that kind of time frame. So having that, just even that heads up is important. Okay. So some of the stuff that we want to talk about were some of these lessons learned, and we're going to start off with on the financial side. And so one of the things that obviously trying to avoid is savings or outcomes that don't match expectations. And so the chart we're showing here is, based on a study that was done. Mac, I know you were involved with this one, so I'll probably have you explain this a little bit. And and just talking about, what the customer's expectations are, if they have a specific return on their investment that they absolutely have to see, and how to, get that information to them in a confident way.
Yeah, this was a client that received a proposal for solar plus storage project in Microgrid to reduce the net operating income of the facility. And sure, a 4-year return on investment sounds amazing. Like, who wouldn't want to do that with tax credits and SCHIP funding, etc. And but so that was brought to me to analyze it again. And when you really go, we had the 15-minute interval data, so we had really good load data. I looked up to the updated TOU tariff rate for this utility, and with the 3 different seasons they have, and the off-peak, super off-peak, super peak, etc., all these different types of rates, I had to incorporate the exact rates for different hours of the day, and which I love how Zendy does this, by the way, and it allows me to edit and create that tariff rate structure with demand. And when we went through the analysis, we found that it wasn't a 4-year payback. It was actually going to be a 7-year payback, which is significantly different. Now, I think a 7-year payback schedule on this is still amazing, but it allowed the client to have his expectations managed, where if they had gone forward with the, expecting a 4-year and then resulted with almost twice as long, well, I don't think 7 years is bad. That's not how you should conduct business. Like, if being held to your promises with these large assets is pretty important. So it was interesting to go through this process and really dive deep with these Homer Grid and Zendy microgrid model optimization software to give the closer to an exact number of what the return on investment was going to be. Also had another client that had a leased system as well, and it was stated in the contract that their target savings was going to be greater than the monthly payments, and they didn't quite understand why their electrical savings wasn't meeting those thresholds. So we took the data and analyzed it and saw what was actually wrong, not only in the design of the microgrid, but also with what was there, how it's being used. And even if it was, even though they could have improved the actual system architecture, the existing system dispatch and how it was operating wasn't optimal. So we kind of discussed and chatted about how to change that algorithm to then incorporate it into the microgrid so that they can get better results and get closer to actually having their savings greater than their monthly payments.
So that was something, that sounds to me, so that's more on like kind of the ongoing analysis and somebody keeping an eye on the actual production, the actual how the system's actually working itself versus even on the front end though.
Yeah, with cost of energy constantly going up, we can do an escalation rate for a utility and even a load escalation rate in the feasibility studies from year to year, but the actual rates that that increase with the utility are going to be different. So every now and then, I think that that analysis should be redone to make sure that the system is still optimized best for that utility and the primary goals. If the primary goals is all financial, it should be analyzed maybe once when rates change or when loads change, just to make sure it's keeping up or it's giving you the most financial benefit.
Sure. So can we go back and talk a little bit about this graph specifically and just kind of what that use case? So you mentioned that somebody had done an analysis, came back with a 4-year ROI. And I guess one is, was there something that triggered needing to look at it deeper? Was it known that was just a really high level and not well-defined process? And then I guess kind of, what we're looking at in terms of this graph and kind of what the key things that were struck you about the way that this was dispatching and kind of how the system would have been utilized.
Yeah, great question. So I just thought a 4-year ROI was pretty quick. Even with ITC and makers and SCHIP funding, it's just a very fast. And since I don't commonly see 4 years, I suggested just reanalyzing it. So what we're looking at this graph is, so the pink line is the battery state of charge, and you can see that it's charging and discharging almost every day. And the point of this one, so this was in an area where the TOU was very high from 4 p.m. to 8 p.m., I think. So you can see in the afternoons that, well, let me go through the colors real quick. So pink is the battery state of charge. The blue is utility purchases. The green is battery discharge, and the yellow is the solar. So you can see when you have the high time of use, which is in the afternoons, is when they're actually discharging the battery. And also the batteries get discharged to ensure that you're maintaining your peak demand here at roughly maybe 1600 kW. So the black line is actually the load profile for the building. So they're now going to have peak shaving from about, at least on these 3 days that's shown, is from 2000 down to about 1650 or 1700. So they'll get those savings. They're discharging they're charging the batteries up with the solar. So you can see in the middle of the day it goes up where the yellow is high. And then the gray line is also, the gray dotted line there means charging the batteries. And then the batteries, and then the pink line drops in the afternoon to discharge the batteries when they are paying the high rates. And in this utility, it's 28 cents a kilowatt hour from 4 p.m. to 8 p.m. or roughly, and then discharging the batteries to get a lot of that financial gain. And even with that constant charging and discharging and checking in on the batteries, best charging rates with their warranty, and then the equipment with the inverters, we want to ensure that we're charging and discharging in a manner where it's going to still meet those life cycles for the battery, and and be there for the lifespan of the projects. Because if your project lifespan is 15 years, it's really easy to make a feasibility study for 15 years and do this. But if you are also reinvesting technologies because you're trying to do a 25-year life to meet the solar panels, then the feasibility study needs to incorporate those reinvested technologies as well. But I digressed a little bit. But those are the colors of the graph, and I hope I answered all those.
That was great. That's very helpful. So, yes, I think some of the big takeaways here. The financial aspect is obviously always going to be a big part of it. If we've done some systems where resiliency was the key, and resiliency, being able to provide power during specific outages, was the goal of the system. But even with that, the financial aspect was important, and having to look at what are those demand charge reductions, what can we do, becomes an important aspect of this.
Mm-hmm.
Are you guys, and I'll throw this to both of you, I feel like we are seeing this, but are basically all the systems that you're seeing go in, are they mixing both the demand response, demand charge reductions, along with some level of resiliency? When resiliency is part, in the equation, obviously. But is that always just something that you guys are seeing and customers are requesting or requiring as part of the systems?
So from our experience, yes, they are providing both, but it also goes to the authority having jurisdiction and permitting. So for resiliency, sometimes it gets more complicated with it when it is either close in front of the meter or behind the meter. But yes, we've seen that the systems procured and deployed are being used for the time of use, and also they are available for resiliency. So we're seeing that more often now.
Yeah, I guess I see a lot of demand, including the demand, peak demand shaving into the financial model, just because it's there anyway. So it might be, like Oregon, Washington, California have a lot of grant programs right now for feasibility studies and implementation of microgrids. And for example, in Washington, a lot of these are for tribes and vulnerable communities. Those tend to be smaller projects, maybe just a 250 or a 125, and they're mostly resiliency projects for resiliency hubs. But part of the requirement of the grant application is they still need to do peak demand shaving. So the financial gain is going to be small, but it's a benefit that the state wants to see to kind of meet their climate impact plan.
Yeah, I would like to add that the systems, they're sometimes they're sized for resiliency, and you're right, Mac. You have the system there already. Why don't you take advantage of the demand response, peak shaving, and you get a little bit of, it might not be a big return because it might be a short period of time, but it's right there.
Mm-hmm.
On another caveat on top of that is that it provides power quality. Sometimes the utility voltages and power is not good. It also provided good stability to the customer in terms of power quality.
Mm-hmm.
That's a great point. Yeah. And I think that's one that I think maybe I've overlooked, but yeah, that's definitely an issue that we've seen. And so, yeah, being able to identify those is an important part of it. And I guess, my question on the demand response is somewhat a little bit, where I sit here in Oregon, those programs you mentioned, Mac, yeah, they are highly focused on resiliency and Oregon specifically, I think Washington as well, our demand charges are relatively low when we compare to, California and other locations. And so, yeah, the numbers aren't always huge, but they're there, like you guys both said. Okay. So we'll talk a little bit about some of the equipment. So lessons learned around the equipment, and Roberto, from your perspective as a manufacturer, I think you had some good input here. But some of the things that you have to take into account we're showing a plan view here of an electrical room where some equipment was going, and so I think one of the things really has to be considered, and this is where getting conversations going with the manufacturers early and often, size change, physical size change, current size change, power, the change in the power output or something of the array or the inverter, things like that can have big impacts. And I guess, can you speak to, Roberto, have you had projects where you've seen this happen, or, being able to be in those conversations, be able to mitigate some of those problems early on?
Yeah, we have both. We experience customers that we absorb the change of cost for them. Depends on the relationship and how big is a project. Sometimes we've done systems that part of the components already approved to be installed, they were discontinued, and they were procured, and we experienced that in the past 2 or 3 years because of COVID. That was something I think everybody experienced. We were committed to a construction schedule, and some components were ordered, and instead of months, it got delayed more than a year and a half to arrive. That created an issue from the original study, from the original permitted plans, to change to alternate components that, even though they're certified, they're approved to be used, it changes the scope of work because of size or space requirements. So sometimes it's out of customer hands, sometimes it's out of our hands. But yeah, we experience sometimes that equipment sizing because of change of technology, discontinued components, or delays.
Yeah, and so I think one of the other things that, kind of this is repeating that same thing a little bit, but we were talking previously in Mac, you were, noting on a specific project, some of those size, some of that spacing requirements. And those are, as you can see here, even in this image, we have specific setbacks and we have specific things that we need to do. In this specific project, we were having to install things inside of a specific electrical rooms. Everything had to be indoors. And so all of those sizing things became very important. But I think there was you had a system where the manufacturer actually was able to do a great thing. They were able to increase their capacity, or they were able to increase the density, the power density of their units. But that had a cascading effect of now you were in NFPA 855, different spacing constraints.
Exactly. Yeah, like there's a 600 kilowatt hour limit, and we were like, for example, within that limit first, and then until the capacity of the batteries increased, and then the battery containers were combined were greater than 600. So then we had to separate them out with the 10 feet, which then of course you've got underground conduit. Maybe your maintenance pad is going to be larger, or maybe doesn't actually still fit in the same location. You're going to have to find new locations. So yeah, definitely knowing your equipment, or being able to see if there's any going to be future changes with the equipment is helpful. They're also just having equipment that is has gone through all the certifications. So when you're actually going for approval from the AHJ, you don't have those kind of hurdles. And UL 9540A is a big one, and having, whether it's fire suppression or that UL listing, just making sure that the products also assist in pushing your project forward.
Yeah, the listing aspect of it is really important, and that 9548, having that testing, being able to get that from the manufacturers is an important one. That's one that I've talked about quite a bit when we started talking about codes and standards and getting into it. So, as of the 9540A will be an absolute requirement relatively soon, as 855, the newer 855 is adopted throughout the US and the new fire codes. But right now it's something that you still have to go out and be able to get and interpret. So that's an important one. One that we talked about a little bit previously, and I wanted to just, Roberto, you had some really good points on this whole thing, was isolation transformers. So getting into equipment, we could spend a lot of time talking about any individual piece of equipment, but one of the things that our team has been seeing a lot is the need for these isolation transformers, how to spec those. And as we were talking about that, Roberto, you pull up off the top of your head, you just listed a bunch of, different requirements that might be out there. So can you talk to us a little bit about, kind of high level, what people might run up against with that?
Sure. Basically on systems that are three-phase, and we're using, NMC chemistry batteries, lithium-ion batteries. The combination of the requirements from the batteries and inverters that are based on the common mode voltage requires that isolation transformer to protect both equipment, the batteries and the inverters. So that isolation transformer helps filtering those noises, harmonics, and basically the common mode that the batteries cannot withstand because of all the switching that is happening on the load side of the transformer. So looking into big systems, three-phase specifically, that combination of the inverter and the batteries are ungrounded, they require that isolation. Right.
Yeah, and so it's just and kind of speaking to the complexity of these systems and the differences, for those we've been in the PV industry for a long time, we've kind of gotten a little bit spoiled, I guess you could say, in the sense of, the inverters are taking care of all this stuff. They've got the 1741 listing, all that. Basically, you put that equipment in, do your interconnection, things, things are, I don't want to say easy, but they're not nearly as difficult as when we start talking about now. You have this isolation transformers and things like that, making sure that your inverters are able to meet those surge capabilities that you talked about earlier, Mac, and all those kinds of things. So it kind of gets into back into our early days of off-grid type stuff, some of the things that we have to think about that we had gone away from.
Yeah, correct. Once we bring that conversation, in the beginning of the design phase, and we explain, because sometimes customers, let's go like, oh, we have a 480 volt system coming from PV. They want to AC couple everything. The inverters have the 480 volts output. So, they are omitting that isolation transformer. And that's a big piece of equipment sometimes that can, impact the financials, impact the construction schedule. So, having that conversation, that technical conversation with manufacturers to bring up, the specific components needed is very important.
Yeah, I haven't looked in a little bit yet, but I was hearing not so long ago, transformer lead times of, even up to a year in some cases. So, so this is, not something you can decide that you need to get and run over to the supply house the day of and grab kind of thing. So, making sure that you're planning for that is important.
Correct.
All right. Okay. And so I think the last lessons learned here we were going to talk about was, resiliency targets, and we'll get into this graph here in a moment. And one of the things, really, Mac, as we've talked, you've opened my eyes and making me think about this is, thinking about the lifespan of the project and the degradation of the components that we have. And so, can you talk to us a little bit about, kind of your approach on that, what you're looking at and what you're thinking about?
Absolutely. Yeah. So if the lifespan of a project is 15 years and you have this resiliency target, you also need to make sure that in the year 15, you're still meeting that resiliency target, right? So with module degradation, battery degradation, load escalation, are you designing the system correctly with that multi-year analysis to ensure that you're meeting that target for the client in year 15? And part of that is not just all your inputs into Microgrid or Zendy, but also after that's done, analyzing it. And like for example, can I get into this graph real quick?
Say again?
Can I get into this graph?
Oh, yeah, absolutely.
So I like this graph because it's a good example. Sure, you could potentially meet your resiliency target. So here in this one, the yellow is grid purchases. So there are none. This is when there's actually a power outage. And the light blue is the state of charge of the battery. So this graph, of course, was chosen for a specific purpose, was to say you're still meeting the resiliency target that year. But if you see on June 13th in the middle, the batteries are charging and discharging about 6 times at a pretty heavy and aggressive charge discharge rate. Well, just because that heavy charging discharging, that's going to reduce the lifespan of those batteries. And even if you're at a 1C discharge rate, you got to check the warranty of the battery to make sure that the asterisk that they put on that warranty means that you can still actually do that. Does it reduce the total life cycle? And then will it still be able to meet that target at year 15? But my main point is taking the optimization analysis, but then diving deep into it yourself, or the consultancy should dive deep into it with using knowledge about the products and the manufacturer and real world experience to see if it's really still a good system architecture and that can meet that resiliency target.
Yeah, and so this was interesting. This was part of the Homer analysis, and so being able to go through and understand what does this actually mean, and like you said, how yes, you can meet it, but at what cost, I guess, or at what impact, not necessarily what cost, but what impact to the overall equipment. And one of the things I really like there is thinking about this resiliency. If we're designing it for a 15-year life, can it meet its stated goals in year 15? So if the batteries have been taken down and it the capacity of those batteries is reduced, then that's an important aspect. So we might need to, I don't want to say oversize, but we need to take that into account, install a bigger battery bank if that's indeed going to be the case.
And this also goes back to Roberto's earlier comment of like defining that use case, and like whether is the system after commissioning going to operate the way that the client expected, and then after it's being operated, if the batteries are getting charged and discharged 3 to 5 times a day instead of just once a day, then you didn't clearly define that use case and then bring that into the optimization.
Correct, Matt. And we had that experience already. We deployed a system to be able to do just black start capabilities with very high power discharge for a very short period of time. And after the system was commissioned and working, they were using the system the other way around. They were charging and discharging the batteries a couple of times a day. On the other hand, we also have systems that they were supposed to be used for peak shaving, and they were not receiving the commands to do the peak shaving at the specific time, which set the batteries being there without any power cycling. And it's also good for the state of charge, state of health, that the batteries are moving, from charge and discharge during that period of time, and not setting the batteries there, not doing nothing for a longer period of time, So it's very important to understand the application and use those battery the correct way.
Great. So we had actually a couple of questions specifically around financials and resiliency projects. And so first one, Brian was asking on resiliency projects, are you able to estimate the savings that include those into the feasibility study and IRR? And this question came in right as we were leaving the financial section. So Mac, I think that's probably a great one for you. I think I know the answer, but I'll let you go ahead.
Yeah, resiliency is a hard thing to quantify. For some clients, you can, like if they lose like a work shift or they lose product, then you can specifically quantify that. But it doesn't really go into my financial model often. It can, but then that's an intimate discussion with the client. If it's, including the financial benefit of having a resiliency hub, et cetera, would be a hard one. But if it's directly affecting profitability of a company, we can incorporate that for sure. But as for the analysis, it takes into account, the PV production, et cetera, and then those savings anyway.
Okay. Cool. And have you heard of this Clean Coalition's value of resilience method? Is this something that you're aware of?
Mm-mm.
Okay. So Craig just points out that Clean Coalition says it's a super straightforward value of resilience methodology. So sounds like it's maybe something that can look out. Maybe worth looking at.
Yeah.
Okay. Whoops, went too far. So the feasibility study. So we're getting close to the top of the hour, so I'm going to be respectful of time here. And I know our guests have other things going on, so we need to try and do our best here to wrap up. But feasibility study, kind of what you get. And so, when we talked about this, when we were talking about this before, the financial model, there's a lot that can go into it. But I guess typically, Mac, what are you, high level here, what are you seeing that is being required to include on those?
For the financial model?
Yeah.
For the whole system dispatch and your savings from the electricity, from the utility, whether it's production or peak demand shaving, if it's DR programs that they might have. I like to present everything in an IRR or a net present value. But if you have cash flows in and out that are not periodic, equally periodic, then you can do an XIRR as well. For the financial model, we include what's the cost of money if it's going to get financed. and include that in the financial model as well. And those would just be conversations with the client on that aspect. But how we present it, is a little bit different, whether it's grant funded, if it's private funded, if it's finance, or it's energy as a service, etc. But that's definitely where the fun gets happening, I think, in the financial model for me.
Okay. And then this logistics roadmap, I mean, Roberto, we were talking about that yesterday, and it this is a real thing. I mean, construction, if you delay construction, things like that. And I think you even had a good example of, getting your net metering agreements, things like that in place. And so that's another one that should be laid out within the feasibility study.
Yeah, that's true. Sometimes also construction processes, like, big crane units or construction equipment. But yeah, in terms of components lead time, we had a project actually that we had some components that delayed the interconnection of the battery energy storage. But we were able to bring up live the PV, which brought the benefit to the customer from the net metering of the PV without the project being 100% complete. So that logistic, is a good part of the feasibility study.
Yep, great. And then this dispatch model, I mean, we looked at the previous slide that we were looking at, talking about or showing that, how the different resources were going to be dispatched. And I think that's an important one to look at and really analyze and make sure that it makes sense, right? It's, yes, like Max said, it can do what it's supposed to be doing, but is it doing it in as efficient way as possible, and making sure that all of the resources are working together. Conceptual designs, the layout, single line design, single line drawing, interconnection details, controls details. The controls are always one of those big things. So, kind of keeping that in mind, and then equipment options, and then conclusion. So, I would say that we're highlighting here some of the key things that would be part of what you get out of a feasibility report that you should be looking for when you're going through and doing these. So then finally, the key takeaways. I think one of the big ones that we talked about is these perceived challenges. Feasibility study is going to take time. It's going to take money. It's going to delay the project. But on the flip side of that is, we've seen real challenges. If you don't do it, then there's probably going to be changes. There's going to be things that are going to get in the way of all this. So, making sure that you're choosing those components carefully and investing in doing, quite honestly, doing feasibility studies on the upfront on that side. So, this is something that I think everybody from, on the design side all the way through engineering, construction, commissioning, I think everybody would agree, having this component of the feasibility studies on being done for the entire system. Okay. So we're right at the top of the hour. So, I wanted to take a moment. Thank you, Mac. Thank you, Roberto. Here's our contact info. I saw some folks had some questions specifically. Craig, you were asking some stuff about Roberto specifically on ELM. So there's a way for you all to get a hold of all of us. Ari, you asked a question early on, and so I'd be happy to talk to you directly about those, the RFQ question you had. So you're welcome to reach out directly to us. And I guess in the closing, in the last moment here, I don't know if there's anything Roberto or Mac you wanted to say, but I really appreciate your time. Yeah,
thank you very much for letting me join.
Yeah, thank you, Ryan, and thanks everybody for joining.
Awesome. Okay, well, we'll call that a wrap on this one. I appreciate everybody's time and attention. And if you have any specific questions, feel free to reach out and be happy to talk.
Thanks.
Thank you all.
Take care. Bye.